Alright everybody, welcome back. This is the third and final video related to Unit 2, Section 2 of AP Calculus, defining the derivative of a function and using derivative notation. In this video, what we're going to do is we're going to look at how we can find the equation of tangent lines and normal lines to curves using the information that we've previously covered in this particular section. So we start with, a tangent line, the definition, a line that touches a curve at a point without crossing over. It is possible that the tangent crosses over the curve in a location not near its point of tangency. For instance, this line right here is tangent to the curve at the point A, f of A, in spite of the fact that it crosses over here later on. It only touches one point in the immediate vicinity of that point of tangency. So in order to write the equation of a tangent line, we're going to need two things. We're going to need both coordinates of the point of tangency and the slope of the curve at that point. And then once we do that, we're going to use point-slope form of a line. Hopefully you're all familiar. I wish they spent more time on point-slope form of a line in earlier classes, because when you get to AP Calculus, it's really our preferred form of a line. But point-slope form of a line is y minus y sub 1 is equal to the slope times x minus x sub 1, where the line goes through the point x sub 1, y sub 1 with slope m. So when we're going to find the equation for a tangent line, we need both coordinates at the point of tangency, that's going to be our point, and then we need the slope of the curve at that point, that's going to be our slope. And we're going to find that using our derivative. Okay, so let's go ahead and we'll do example 5 here. Find the equation of the line tangent to the curve y equals 4 over the quantity x minus 2 at x equals 5. So usually when I'm finding the equation of a tangent line, the first thing that I do is I go right ahead and I find the coordinates of the point of tangency. That's always my first step. I usually just do it up in the top right-hand corner here. And so I'm going to substitute 5 in here for x. And that gives me 4 over 3. And so our tangent line goes through the point 5, 4/3. So that's our point of tangency. Okay, the other piece of information I need for this tangent line is I need the slope of the curve at x equals 5. And so I'm going to find f prime of 5. So I'm going to do that using the limit of the difference quotient. I'm going to take the limit as h approaches 0 of f of 5 plus h minus f of 5 all over h. And so now I'm going to put 5 plus h into my function. And I'm going to put 5 into my function. And I'm going to go ahead and simplify. This is a limit as h goes to 0 of 4 over 3 plus h minus 4 over 3 all over h. Now, since I have fractions inside of fractions, what I want to do is I want to clear those fractions out of the numerator. And the way I'm going to do that is I'm just going to go ahead and multiply the numerator by both of these denominators. And when I do that, in order to preserve the value, I'm going to also multiply the denominator by both of those values. And when I do that, the 3 plus h, when I multiply this by the first term, the 3 plus h cancels out, and so the first term of my numerator becomes 4 times 3, which is 12. And then when I multiply that through times the second fraction here, this time the 3 cancels out, and so this becomes 4 times the quantity 3 plus h. And my denominator is just going to be h times 3 plus h times 3. All right, now I'm going to go ahead and simplify. So I've got the limit as h goes to 0 of 12 minus 4h all over h times 3 plus h times 3. And so that becomes the limit as h goes to 0 of negative 4h over h times 3 plus h times 3. And now I can cancel an h from both numerator and denominator. And so this becomes the limit as h goes to 0 of negative 4 over the quantity 3 times 3 plus h. And so I can substitute the 0 in now. It gives me negative 4 over 3 times 3 plus 0, or negative 4/9. This is the slope of my tangent line. And now I'm going to go ahead and use that slope along with the point and point slope form of the equation to write the equation of the tangent line. And so my tangent line is going to be y minus the y coordinate of this point, so y minus 4/3 is equal to the slope negative 4/9 times the quantity x minus the x coordinate of the point. There's my tangent line. And I can just go ahead and leave it like that. Don't nuts around with that. I always tell students, there's no benefit for you changing this equation from point slope form to any other form unless it's on a multiple choice section and you're trying to get, to match one of the answer choices. On a free response section, you should always just leave your equation, just stop. There's no benefit. They're not going to be impressed with your algebra and give you extra points. This is an AP Calculus exam, not an AP Algebra exam. So once you've done the calculus, don't bother doing all that extra algebra. You're not going to get any extra credit for it. And if you do things wrong, you could cost yourself points. All right. On to our last example. The normal line to a curve at a point, that's the line that's perpendicular to the tangent line at that point. So if we have a curve, and we draw the tangent line to the curve at a point, the normal line is perpendicular to that one. And so if you think about it, you learned the relationship between perpendicular lines a while back, that the slope of two perpendicular lines are opposite reciprocals. So we're going to go through almost the same process here. We need two things, both coordinates of the point of tangency. But instead of the slope of the line that is tangent to the curve at the point, we need the slope of the line that's perpendicular to the curve at that point. Well, how are we going to do that? We're going to find the derivative, and that gives us the slope of the tangent line. And then if we take the opposite reciprocal of that, that's going to be the slope of the normal line. So other than that, it's very similar. First thing I'm going to do is go ahead and find the coordinates of my point. I substitute negative 3 into the original function for x. And calculate. It tells me the y coordinate is at 6. So this goes through the point 3, 6, or negative 3, 6, pardon me. Okay, then I've got to find my derivative at negative 3. So I'm going to find f prime at negative 3. That's the limit as h goes to 0 of negative 3 plus h, quantity squared, plus negative 3 plus h minus negative 3 squared plus negative 3. All that over h. And so that's going to be the limit as h goes to 0 of 9 minus 6h plus h squared minus 3 plus h minus 9 minus 3. And so all these numbers are going to cancel each other out here. The 9, the minus 3, the minus 9, and plus 3. Okay. And then these two terms, I can combine those like terms, and this turns into the limit as h goes to 0 of h squared minus 5h all over h. Okay, so factoring, because this is going to be 0 over 0, factor out an h. H's cancel. And so this is now limit as h goes to 0 of h minus 5, which is 0 minus 5, or negative 5. This is the slope of the tangent line. And since that's the slope of the tangent line, the slope of the normal line is the opposite reciprocal. So the slope of the normal line is 1/5. And so our normal line is going to be y minus 6 is equal to 1/5 times the quantity x minus negative 3, or x plus 3. Okay? Now, let's pop over here and, check our work. I'm going to justify what we did here graphically. First, we'll go back to example 5, and we're going to look at this curve and its tangent line. So we'll go to Desmos to do that, and we'll type in the curve, y equals 4 over x minus 2. Okay, so there's the curve, and we're looking at the tangent line here at x equals 5. So you see 5 right here. And so if I type in the equation for the tangent line that we found, y minus 4/3 equals negative 4/9. Oops. Forgot to get out of that fraction. Equals negative 4/9 times the quantity, x minus 5. And boom, you see that this is the tangent line to the curve at x equals 5. Right there's 5. Boom, that's the tangent line to the curve. Okay, let's go back to the normal line example, example 6, and we'll plot that function. So let's go back to Desmos. And we've got y equals x squared plus x, and then our normal line, let's go find y equals x squared plus x, there it is. And then my normal line is y minus 6 equals, and this is the normal line at x equals negative 3, so I'm going to drag it over here and make sure I can see the curve at negative 3. So we've got y minus 6 equals 1/5 times the quantity, x plus 3. And this is the normal line to the curve. So that means it goes through this point, negative 3, 6. Notice it goes through that point, negative 3, 6. And it's perpendicular to the curve at that point. All right, this is the end of this video and the end of section 2 of Unit 2 of AP Calc. Hope you enjoyed it. I'll see you all next time. Have a great rest of your day.